As we've seen earlier in this course, the fact that every natural number greater than 1 can be factored uniquely into a product of prime numbers is an ancient and fundamental theorem upon which all of basic number theory rests. In this lecture, we'll return to this ancient notion of unique factorization, first proved by Euclid, and discover some of its important ramifications within the realm of Diophantine equations. We then will challenge our imagination to consider a world of number that does not exhibit the property of unique factorization into primes. The reality that some collections of numbers can be factored into primes in more than one way is at once surprising and revealing. These discoveries will lead us to the notions of algebraic integers and generalized prime numbers. Armed with these new ideas, we'll describe Gabriel Lemai's failed strategy to prove Fermat's last theorem and offer an overview into the theory of Ernst Kummer that was inspired by Lemai's failed attempt. This stunning and powerful theory gave birth to what we call today algebraic number theory. Given that this important area of number theory has its roots in factorization properties, it is perhaps not surprising that these abstract ideas now have practical implications within the modern theory of cryptography. Well, we're going to have some fun now, because I want to first open this discussion by recalling Euclid's famous result, now known as the fundamental theorem of arithmetic. It states that every natural number greater than 1 can be expressed as a product of prime numbers, and, more importantly, that this factorization is unique, except for possible rearrangement of the factors. Now, we prove that every natural number greater than 1 can be expressed as a product of primes by adopting a divide and conquer method. For example, recall that we saw that 12 can be written as 2 times 6, since 12 itself is not prime. And so we divided and conquered it into smaller natural numbers. The 2 is prime, so we leave that alone. The 6 is not prime, it's composite. We break it smaller, and we see 2 times 3, and thus we see a total 2 times 2 times 3. And we prove that for ourselves, that every natural number has that property, because we could proceed in the similar fashion. Now, you might remember that we didn't, in fact, prove the uniqueness of this factorization. Now, in our previous example, we have that 12 equals 2 times 2 times 3, but also could be written as 2 times 3 times 2, and also as 3 times 2 times 2. So we could rearrange the factors, but in all factorizations, we always have 2 factors of 2 and a factor of 3. Well, as intuitive as the uniqueness feature might appear, we'll soon actually discover for ourselves that this property should not be taken for granted, and that's where the fun's going to be. However, now I want us to realize that we can apply the fundamental theorem of arithmetic to find integer solutions to certain Diophantine equations. Now, to illustrate this method, let's consider the Diophantine equation x squared minus y squared equals 5. Now, let's note that the left-hand side of this equation can actually be factored. X squared minus y squared actually equals the quantity x plus y times the quantity x minus y. So our equation is x plus y times x minus y equals 5. And this is quite convenient, because if there were integer solutions to this equation, then we would have the product of 2 numbers equaling the number 5. However, since 5 is a prime number, the only possible pairs of integers whose product yields 5 are 5 and 1. 5 times 1 is 5. 1 and 5, again, order doesn't matter, and they're negatives. -5, -1, a negative times a negative, remember, is a positive, so that would be 5. And lastly, -1 and -5. Take their product, and we see 5. Well, if we consider the first pair of possibilities, namely 5 and 1, then we would actually obtain a pair of simultaneous equations. The first factor, x plus y, would equal 5, and at the same time, the second factor, x minus y, would have to equal 1. Therefore, the product would yield 5 as desired. Well, if we take these two equations together and add them, then we would discover that the y's would drop out, and I'd be left with 2x equals 6. And if we divide both sides by 2, we'd see, of course, that x equals 3. Now remember that x plus y equals 5, and so if x were to equal 3, then we would see that y must equal 2. And hence we found an integer solution. And we can check that indeed 3 squared minus 2 squared equals 9 minus 4, which is 5. So the factorization gave rise to a solution. Well, considering the other 3 cases that we could have, namely 1, 5, and then the negatives, we find that all the solutions to this equation are given by x equals positive or negative 3 and y equals positive or negative 2. And we compare these positive and negatives up in all possible ways, and thus we see 4 integer solutions, namely 3, 2, negative 3, 2, 3, negative 2, and negative 3, negative 2. And so we see exactly 4 solutions to this, and factoring uniquely into primes is what saved the day. Well, in fact, unique factorization into primes also allows us to demonstrate that certain other Diophantine equations have no integer solutions. So this method can be used for both equations that have solutions and also equations that don't. Now, to illustrate this method, we consider a modified version of the previous Diophantine equation. X squared minus y squared now equals 6. Again, we factor the left-hand side, and we see that we have x plus y times x minus y now equals 6. And we proceed in a similar fashion. Now, in this case, there are many ways to factor 6 into the product of 2 integers. In particular, 6 equals 1 times 6, 2 times 3, 3 times 2, and 6 times 1, together with all their negatives, because we could have, for example, negative 1 times negative 6, and so on. So there's a total of 8 now, 8 possible factorizations of 6 into integers. Notice that with integers, we're allowing the negative numbers as well. Well, if we consider each of these possible factorizations, we'll discover that none actually lead to integer solutions to the original equation. For example, let's consider the possibility that the first factor, x plus y equals 3, and the second factor, x minus y equals 2. Notice their product would yield 6. Now, if we add these two equations together, we discover that 2x equals 5. And if we divide by 2, we see x equals 5 halves, which is not an integer. Similarly, we can go through and verify that the 7 remaining possible factorizations do not lead to any integer solutions as well. Hence, this equation has no integer solutions. Well, these methods illustrate the importance and utility of unique factorization of numbers into primes, in this case, within the context of finding integer solutions to Diophantine equations. So, within the context of Diophantine equations and beyond, we've seen the power of the arithmetical structure of the integers. Beyond the all-important property of factorability into fundamental building blocks, namely the primes, the integers satisfy, in fact, many axioms of arithmetic that we just take for granted as we solve equations in our everyday lives. For example, the sum of any 2 integers is another integer. And we say that the integers are therefore closed under addition. Any 2 integers, add them, you get another integer. There exists an additive identity element, namely 0. Adding 0 to any number does not change the value. That is, the identity of the number remains the same when you add 0. And for any integer, there exists another integer, call it the additive inverse, so that their sum always equals 0. The second number is usually called the negative of the first. For example, 3 plus negative 3 yields 0. Moreover, we can group numbers in any way we want in order to add them. For example, suppose we have 3 plus 5 plus 2. We could first consider the 3 plus 5, add that and get 8, and then add the 2 to get 10. Or we could group the second terms together first and say, well, 5 plus 2 is 7, and now when I add the 3 out in front, I still get 10. And this property is actually called the associativity property of addition. Well, of course, we also have multiplication running around, which we can use with our integers. And noticing that the product of any two integers is in fact is another integer shows that multiplication is again closed and also associative. Furthermore, multiplication and addition work together in a harmonious fashion, and we call this property the distributive laws. And they include the property that if I have A and I'm multiplying it by the quantity B plus C, then that's the same thing as first taking A times B and adding it to A times C. You can distribute the A. It's these properties that allow us to solve simple algebraic equations, such as x plus 5 equals 7, for example. Well, more generally, any collection of numbers that satisfies all these properties involving addition and multiplication is called a ring. That's the mathematical abstraction of the integers. And this, in fact, area is actually studied in great depth, perhaps not surprisingly, in what is called abstract algebra. Okay, well, let's now have some fun and consider an entirely new universe of number. One with which we've already actually become familiar with, the collection of even integers. 2, 4, 6, 8, together with their negatives, and 0. For now, let's view this collection of numbers as our entire universe of numbers. In other words, we'll pretend for the moment that the odd numbers don't even exist. Okay, so let's just have some fun. Now, we can actually verify that the collection of all even numbers is another example of a ring. If we add or multiply two even numbers together, the answer is an even number, so it's closed. And those operations are still associative and satisfy the distributive property. We also still have the additive identity 0, that's considered an even number, and every number has an additive inverse. For example, negative 10 is the additive inverse of 10, and both are even. So, the even numbers form a ring. Well, let's now consider factorization in this new ring. Well, we can now consider the so-called prime numbers within the context of this number system. In other words, those even numbers that can't be factored any further into the product of numbers from our world of number. Now, of course, 2 is a prime in this context, because 2 can't be factored into two smaller pieces. But now we're going to see some unfamiliar primes as well. For example, now the number 6 is a so-called prime, because we can't factor 6 into the product of two smaller even numbers. You see, you want to split 6 apart, don't you, as 2 times 3, but we have no odd numbers. So 6 can't be broken apart into two smaller even numbers, therefore 6 is a prime. The number 12, on the other hand, is not prime, since we can, in fact, write it as 2 times 6, and notice both of those are two smaller even numbers. Remember, we're always staying within the world of even numbers now, within this particular ring. Thus, the first few so-called prime numbers within the ring of even numbers are 2, 6, 10, 14, 18, 22, and so on. Kind of funny to think of the numbers such as 14 and 18 as being prime, and yet I defy you to try to factor them into two smaller even numbers. Notice, for example, that 20 is a composite number in this context, since we can write it as 2 times 10. Again, two smaller even numbers. Well, adopting the divide and conquer strategy that we previously employed, we can discover that every even number is either one of these newfound primes or can be expressed as a product of even primes. The exact same idea that we employed in with the classical natural numbers will work here as well. However, do we still have unique factorization within the prime factorization? Well, let's consider the factorization of 24. Well, it can be expressed as 2 times 2 times 6. And notice that they're all primes. 2 is prime and 6 is prime. Sorry. And except for the rearrangement of these terms, this product is unique. There's no other way of writing 24 as a product of primes in this context. However, let's now consider the factorization of 36. Well, it can be expressed as 6 times 6, which notice is in fact the product of two primes because 6 is prime in this context. However, it can also be expressed as 2 times 18. And 18 is, in fact, a prime here. Thus, we see two genuinely different factorizations of 36 into primes within this context. Isn't that neat? Well, hence, we conclude that this ring of numbers does not exhibit the unique factorization into primes. Factorization into primes, yes, but unique, no. Well, while the ring of even integers, a ring that we just discovered does not enjoy the property of unique factorization into primes, is not particularly useful in practice within the study of number theory, there are other rings of integers that are extremely important. These new rings of integers generalize the ring of ordinary integers in a different direction. These rings grow out of complicated solutions to certain special equations. For example, if we consider the solutions of the equation x squared equals -5, then we'd see that x is positive or negative the square root of -5, two imaginary numbers. Well, we can use the square root of -5 to actually create an entirely new ring of integers that include the traditional ones. In particular, we consider the collection of all numbers having the general form a plus b times the square root of -5. And here, a and b are ordinary integers with which we're familiar. So, for example, 2 plus 3 times square root of -5. That's one of the objects in this collection. -1 plus 8 times square root of -5. Another example. Even -19 times the square root of -5 is in there, because I can always write that as 0 plus -19 times the square root of -5. So anything of that form fits into this category. And even the number 7 itself is inside of here, because I can write it as 7 plus 0 times the square root of -5. So these are all examples of integers, and you can see they contain within them the usual integers with which we're familiar. Well, while we won't prove it here, it can be shown that this collection satisfies all the properties required to make it, again, a ring, this idea of a ring. And thus, we can view it as a generalized ring of integers. In fact, this collection is an example of what is known as a ring of algebraic integers, because the numbers arose out of solving an algebraic equation. Well, just as with the ordinary integers and with the even integers, we can identify the so-called prime numbers within this ring. In other words, the fundamental building blocks within this new collection of algebraic integers. Identifying which numbers here are prime and which are composite, by the way, is extremely tricky business, especially in this context. For example, some of the new primes are just certain regular traditional primes, such as 3 and 7. However, other primes look more exotic. For example, the numbers 1 plus 2 times the square root of -5 and 1 minus 2 times the square root of -5 are in fact both primes in our new ring of algebraic integers, although we won't verify that for ourselves. Well, using a much more elaborate divide and conquer technique, it's been shown that every algebraic integer in such a ring is the product of such primes. Now, technically, just for a moment, remember that we don't include 1 when we consider the natural numbers, when we're considering prime or not prime and so forth. And so here, we also have to exclude 1. And in fact, there are other peculiar numbers like 1 that we exclude as well, and those are called units. But let's not even worry about that. The idea is that every number within this particular ring can be factored into primes, and we'll throw away 1 and things that look like 1. However, in general, we cannot guarantee the uniqueness of this factorization into primes for a ring of algebraic integers in general. For example, in our ring involving the square root of -5, we can see that the number 21 on the one hand equals 3 times 7, the product of 2 primes in this context. But on the other hand, I'm now going to claim that 21 also equals the product of 1 plus 2 square root of -5 times 1 minus 2 times square root of -5. In other words, the product of 2 genuinely different primes. Well, I want to confirm this assertion for ourselves right now, and all we have to do is just carefully multiply 1 plus 2 times square root of -5 times 1 minus 2 times square root of -5. If you don't want to worry about the algebra, great time to take a 2-second nap, but then got to come right back into the fun. Here we go. Or you can just watch me and enjoy. If we multiply these two numbers together, what we see here is 1 times 1 is 1. Then we have plus 2 times square root of -5. Then a minus 2 times square root of -5, which notice magically, by the way, will add to give 0. And then minus 4 times the square root of -5 squared. Well, the square root of -5 squared is just -5. And so I see -5 times -4, which is -20, and which is positive 20, rather. Negative times a negative is a positive. Oops. And then we have that 1 way out in front, and so 1 plus 20 equals 21. We just factored 21 into this product of 2 very funny-looking primes, and we already know that it equals 3 times 7. Okay, nap time is over. We're back. Therefore, what we see is that this ring of algebraic integers does not possess the unique factorization property into primes. Well, armed with this new insight into the lack of unique factorization within this general ring of integers, we now recall that in 1839, Gabriel Lamé produced a very elaborate argument to prove Fermat's last theorem in the case n equals 7. In other words, he proved that the Diophantine equation x to the 7th plus y to the 7th equals z to the 7th has no natural number solutions. That same year, he announced that he proved Fermat's last theorem in general. In other words, he claimed to have a proof showing that for any natural number n greater than 2, the equation x to the n plus y to the n equals z to the n has no natural number solutions. Well, his clever idea was to assume that there were integer solutions to Fermat's equation and then factor the left side. Recall, for example, our proof that the equation x squared minus y squared equals 6 has no natural number solutions. We pretended there were some natural number solutions, and we factored x plus y times x minus y equals 6, and then saw that there could be no factorization of 6 into two integers that satisfied this particular equation. So Lemay does the exact same thing with the Fermat equation. However, to factor Fermat's equation, Lemay had to use algebraic integers rather than just the ordinary integers. Now, after he factored Fermat's equation using numbers from a particular ring of algebraic integers, he assumed that this ring possessed the property of unique factorization into primes that the ordinary integers enjoy. Given this assumption of unique factorization, Lemay's proof was in fact correct. However, the question remained, did Lemay's ring of algebraic integers possess this unique factorization property? Well, we've just seen an example of such a ring that does not have this property. Unfortunately for Lemay, and for mathematics, I suppose, his particular ring of algebraic integers did not possess the unique factorization property either, and thus his proof was flawed. The factorization problem with Lemay's proof was actually quickly discovered by Ernst Kummer. Kummer then tried hard to fix Lemay's proof, since it was otherwise a very clever strategy for attacking Fermat's last theorem. The question remained, is there a way to capture some essence of unique factorization into primes within all rings of algebraic integers? Kummer then made a marvelous discovery about algebraic integers. Kummer proved that even though there are rings of algebraic integers that do not possess unique factorization into primes, the elements of every such ring can be clumped together into packets of numbers, small collections of algebraic numbers. These collections can be combined with operations that are similar to addition and multiplication. In fact, these packets themselves form a ring. In other words, we can perform arithmetic, but instead of performing arithmetic with pairs of numbers, Kummer suggested that we perform arithmetic with pairs of packets of numbers. Really abstract idea. The number now is taken on, the concept of number is taken on by a whole packet of numbers. So you have one packet of numbers, another packet of numbers, and we add them and we produce a new packet of numbers, and so on. Well, he then found that within these packets of numbers, there are prime elements, fundamental multiplicative building blocks, and proved an amazing result. Every packet can be expressed as a product of these prime packets, and moreover, that factorization is unique. In other words, Kummer found a unique factorization property within any ring of algebraic integers, not within the elements themselves, but within these packets of elements. Isn't this incredible? Really wonderful, wonderful result. Well, he called these packets of numbers ideal numbers because they enjoy the celebrated unique factorization into primes. Today, we actually call these packets ideals, and these are known as ideals in abstract algebra. Unfortunately, Kummer's groundbreaking discovery about the unique factorization into prime ideals was not enough to complete the proof of Fermat's last theorem. However, Kummer's work did launch an entirely new branch of number theory known today as algebraic number theory. His work had far-reaching consequences in a variety of related and unrelated areas and continues to be influential today. In fact, algebraic number theory has connections with cryptography since, as we've seen earlier, encryption issues involve factorization into primes. Thus, Lemay's problematic proof was extremely valuable in inspiring Kummer's original work that, while it did not resolve the issue for which it was intended, did change the face of number theory forever. And I just want us to close by celebrating the importance of and power of making mistakes and failing. For every false attempt, every failed start, in fact, could lead to a new understanding of nature. In this case, a new understanding of number.